Hi guys, Mr. Hyatt here. This is part 2 of the Chapter 4 AP Environmental lecture. So we're picking up looking at indicator species, talking about the same stuff I talked about with the amphibian case study at the very beginning of part 1. So we use these species basically like a smoke alarm, like it says on the screen. We see that amphibians are passing away, we know that something is going on. Their presence or absence indicates the quality of the environment. So sometimes things will show up if we've got the right pollutants. They need a certain type of metal in their diet. So if there's a pollutant that they need, they'll show up. Sometimes it's that these things are dying, or maybe they're just flying away, or they've migrated somehow, some way. So we know that something is going on with the environment because these indicator species are changing. So 4.3 deals with evolution. You'll notice it's one section of one chapter, so it's not a major topic here in environmental science, but it definitely comes up here in the biodiversity chunk. So hopefully you understand the theory of evolution and natural selection. Basically, it explains how life changes over time due to changes in the genes of the populations. You might not have made the connection as freshmen between evolution and genetics. That's something you need to keep in mind, and you need to make that connection here in APES. Population evolution occurs through gene mutation. I like to say to my freshmen that mutation provides the raw materials for evolution. Mate choice and survival drives natural selection. Excuse me. So don't confuse natural selection and evolution. Evolution just means things are changing over time. Natural selection is going to be, do you survive and make babies? We've got evidence from fossils. We've got lots of genetic information. We've got evidence collected recently from things like genomic studies, from things like looking into overprescription of medications, pesticide resistance, the emergence of things like MRSA. These are all real life and modern day examples of evolution and natural selection in action. Like I said, genetic variability is key. Mutations provide the raw materials for evolution. If we're all the same, there's no differential survival or reproduction. And both of those are requirements of evolution. So some people also confuse adaptation and evolution. Adaptation is not the same. If I move to Antarctica, I might grow some extra hair. I'm going to adapt. I'm not, or for example, I might just by nature be a hairy guy. And if I move to Antarctica, I'm going to be healthier, warmer than somebody who doesn't have a lot of hair. Again, an adaptation is something I already do. I might do it a little bit better. Evolution is coming up with a new trait, or the emergence of a new trait. Genetic resistance is going to be, like you see here, ability to tolerate chemicals designed to kill the population. That's what we see with overprescription of antibiotics and pesticide resistance and all of those sorts of things. Sorry, skip the slide. Here's evolution by natural selection. Okay, so I read some research in 2003 probably that talked about hand sanitizer. Think about right here, these are your hands right now. You've got some bacteria that's normal and you've got a couple of resistant bacteria. You apply hand sanitizer, it kills 99.9% of bacteria, or so the label says. Takes out all the blues because they're vulnerable. The 0.1% are going to be these resistant bacteria. After some time passes, we're going to accumulate some of this quote-unquote normal bacteria. But these guys, you've now eliminated all their competition. They've got plenty of food, water, shelter. They're going to make lots of babies. You're going to be getting many more resistant bacteria than you are the normal bacteria. Over time, that leads to something like MRSA. Excuse me. Organisms can only adapt to a change in the environment if they already have those traits. They might be turned on, they might be turned off, they might be exacerbated, so you express something more than you did previously, but it's a genetic trait that you already have. You can't suddenly sprout snowshoes for feet or sprout wings to fly home or something along those lines just because that works. You know what I'm saying? Because that would be an advantage. Even if this trait is present in a population, like there was a crappy movie that came out when I was a kid called Waterworld with Kevin Costner, and he had gills for ears. He was born with gills for ears. Well, that's a great adaptation in a world that's flooded, which was the scenario for the crappy movie. But it's still, he can't make a whole population of babies in a lifetime. He might be able to make, if he's some sort of prolific king, he might be able to make 100 babies in a lifetime or something like that. But even that's not going to drastically impact the overall population. So it takes a whole lot of time is kind of what I'm getting at there. Okay, so that was the evolution chunk. So factors that impact biodiversity basically are going to be changes. We do a lot. We cause extinction of species. We tear down habitats to build cities, to heat our homes and things along those lines. So we affect them in many ways, mostly negative. Sometimes we save species, but a lot of times what we're doing when we're helping species is undoing things that we've done previously. So how do new species arise? It's a process called speciation, and it's when one species becomes multiple species. You've probably learned about Darwin's finches. That's kind of the classic example of speciation. One species settled islands, they accumulate mutations. Eventually it gets to the point where those species are so different that they can no longer mate and produce fertile offspring, and we have subspecies. For that to happen, we have to have some sort of isolation. In terms of Darwin's finches, we started with geographic isolation. The birds just couldn't get to one another. They're on different islands. Over time, you become reproductively isolated. So enough mutations accumulate so that even if you put those two birds together, they couldn't make a baby. The parts wouldn't fit together, or the chromosomes wouldn't line up. There'd be some sort of pre- or post-zygotic isolation. Geographic isolation, Arctic fox, gray fox, great example of that. Darwin's finches, another good example of that. But eventually, geographic isolation is going to lead to reproductive isolation. So this is an odd title for a slide. I fully admit that. All species eventually become extinct. Extinct, of course, we know, means gone, not extirpated, extinct. So a species facing crisis may adapt, move, or die. That's pretty much the three choices. Something changes, you can either adapt, you can move and go somewhere where you fit in, or you can die. Endemic species are particularly vulnerable to extinction, like we talked about last week. It's only in one spot or maybe a few spots on the world. It changes, they're not going to survive. That should sound a lot like what I talked about in part 1 with diversity. This species, an endemic species, is not going to be spread across a lot of ecosystems. So, more diversity, you live in more places, the world changes, some of your population is probably going to survive. You live in one place and the world changes, you're probably all in trouble. Next step is to talk about mass extinctions. Of course, we know if it's a mass extinction, a ton of species are dying. We're not talking about 2 or 3 species being wiped off the face of the earth. We're talking about a lot of them. That's kind of contrasted against the background extinction rate. So most of this, we'll notice before modern humans. Things like the dodo bird. Less than 1 species per million just naturally gets outcompeted and just loses. It's not because we've changed their climate or anything along those lines. They just aren't as fit to their environment as another species. Dinosaurs. They got outcompeted. Well, they sort of got taken out, but you get the idea. Often global events tied to major widespread environmental change cause mass extinction. So the dinosaurs are an example there. There was a major change that caused the environment to change, drove off the dominant life force on Earth. The current mass extinction, we're currently in the 6th mass extinction. We're going to talk through some of those on the next slide. But the current mass extinction is, there's pretty strong evidence that we're causing it. We're changing the climate, we're polluting, we're doing things that are messing with a lot of species. Fossil and geological evidence show there have been 5 mass extinctions during the past 500 million years. That's way older than humans. So these mass extinctions have been followed by an increase in species diversity. So basically, think about it this way. There's a whole bunch of dominant life forms. They all die. So now there's all these jobs open for all these other species. Humans, for example. Mammals, for example. Mammals, when the dinosaurs were around, were like moles or voles. They were small creatures that lived underground. The dinosaurs would have eaten them had they come out. Dinosaurs go away, and now mammals can come out from hiding, and they can diversify and become all the mammalian life that we see on Earth today. So after there's a mass extinction, we see radiation events where tons of new species emerge quickly to fill those niches. Like I said, it appears that we're in the middle of the 6th mass extinction, and it's our fault. You see the speciation on average through time stays ahead of extinction, so we're gaining species, but we're not. You know what I'm saying? Like new species are emerging, but we're losing species faster than we're gaining new species. I hope that makes sense. Next up, we select species traits sometimes in artificial selection. We've been doing that for years and years and years. Thousands of years we've been breeding big strong calf and big strong bull, and they make big strong babies. And big strong horse races breed with big strong mares, and they make big strong horse races for the next generation. Then we genetically engineer. We've been doing that for maybe 20 years. We can alter DNA. We can create new species. We can create new types of food. We can create new. We can breed better horses, things along those lines, because we can manually manipulate their DNA. We also can transfer genes between different species that wouldn't interbreed in nature. We can use things like glowfish genes to transport into humans even, and to make things glow, or transport into, sometimes we do it with mice and with pigs and things like that to check for other issues. So there are a lot of things that we can do to manipulate traits. So try to focus on the biodiversity piece. The evolution part of this chapter is definitely secondary to the biodiversity stuff. A lot of vocab, but as often as you can, try to bring it back to biodiversity. How is this impacting biodiversity? How does biodiversity impact it? And what am I supposed to do with it? That's chapter 4.